Now the term periodic means regular and repeating. So periodic table means there's some regular repeating patterns, and we've seen some already. We've seen the electron configurations and how the S2 is always the alkaline earth metals, or the whatever it is, and then it ends P5. We know that is the halogens. So there's some trends there, but we're going to take a look at some additional trends, okay? And so some things that are happening, repeating on the periodic table. One is the atomic radius, the size. So again, if we talk about the radius, we're talking about, say we have an atom, we have our nucleus in the middle, and their radius is, of course, from the center to the outside. Now please understand that, electrons are moving around. So remember, it's not in this orbit going around and around and around the nucleus, but this one red one right here, after it moves, it might be in smaller, so the radius is shorter. So what scientists do is they figure out what the distance between two nuclei are in a compound, and then they can figure out what the radius is. Let me show you what I mean by that. Let's say we have oxygen. Oxygen is O2. So we would have one oxygen molecule and another oxygen molecule. They're sharing electrons, so that's a terrible drawing. Let me, all right, let's see here. Okay, and then here's another one. All right, and you have these sharing electrons in O2. But obviously, you've got your nucleus in the middle of each one. What scientists do is they measure what the distance between each nuclei, because of course you get this orbital, this cloud of electrons, and it could change. So by measuring the distance from one nucleus to the other, and then taking half of that, of course, all right, then they can, of course, determine the radius. Once you know the radius of oxygen, then you could, let's say, put it together with another element. Okay, let's say it was with something else, a smaller atom. You know what the oxygen radius is, so whatever, again, they'd measure between one nucleus and the other, whatever you would have to, you simplify, you just simply subtract the one that you know, excuse me, the one that you know from the total distance, and then of course that would determine what the distance of that. So you can continuously determine radii of different atoms. Now, the radius, let's take a look at it. As we go down a family, this is probably pretty easy to understand, which of course you're going to increase energy levels. And remember, increasing energy levels, we had our nucleus and we went like this, right? We had energy level 1, energy level 2, energy level 3. So it makes sense that as you go down a family, they're going to get larger. So if you compare, francium, which is down on the furthest bottom of the alkali metals, and lithium versus francium, francium is obviously going to be a larger atom. Pretty straightforward with that. Okay. The other trend we want to notice not trend, same trend, but we want to notice what it does across a period. So across a period, as you go from left to right, okay, so as you go left to right, the atoms actually get smaller. Okay, you might say, well, wait a second, there's more protons, more electrons, shouldn't you get bigger? Well, let's take a look at why. You have the same energy level as you go across a period. So here's one. I want to kind of draw them the same. Hopefully they're pretty well drawn the same. We have our nucleus in the middle on each of them, okay? Let's say that one of them is sodium and this one is chlorine. They're in the same family, okay? Now, the energy level doesn't change. Okay, so the energy level doesn't change. Where you have 1, 2, 3, the energy level doesn't change. But Because we have 11 protons in the sodium and 17 protons in the chlorine atom, there are more sucking in the chlorine. All right, think about it. Electrons are negatively charged, okay? And so, in sodium we would also have 11 electrons. Chlorine we would have 17 electrons. My room doesn't get bigger because I put more people in it. If I have a class of 10, I've got a certain size room. If I have a class of 20, it doesn't get bigger. It's still the same room. There's just more people in it. So the fact that there are 17 electrons in chlorine versus sodium doesn't make a difference. Okay, there are 17 electrons, but the room, the energy level is the same. So same room. But why does chlorine get smaller than sodium? Okay, so chlorine is smaller than sodium. The reason is you have more pull on by the protons. So 17 positive charges versus 11 positive charges pulls harder. So you're going to get kind of this shrinking, this sucking in a little bit of the chlorine atom. So as you go across a period, things or atoms get smaller. So larger as you go down. Across a period, I'm going to put more protons, therefore get smaller. Again, that's the reason why. Okay, so there's your periodic table. If I were to just simply down and to the left, down and to the left, down. Oh no, that was up and to the right, up and to the right. Look it up if you're unsure. Down and to the left is where the largest sized atom is. Obviously, the smallest would be up and to the right, up and to the back. So small over there. Francium is the largest, helium is the smallest. Now I'm going to ask, compare ones either in the same family or in the same row. If I ask iron and let's say silver, going down, so those are pretty darn close. Even if it's, let's say I ask for nickel and silver, going down one versus over one, silver is bigger because it changes the whole energy level. Now I won't ask, let's say, scandium and silver because you're going over, 9 versus going down 1. So, but just know that if I ask to compare different elements, let's say, these three, sulfur, bromine, and chlorine, bromine would be the largest atom. Because yes, it's larger than chlorine because it's down below. Sulfur is larger than chlorine. How do you compare those? Well, bromine is down below, so it does go larger. So that's the periodic trend for atomic radius.